Hey there, geometry. We are in Unit 7, Lesson 11, a new way to measure angles. You thought you knew it all about angles, but nope, there's a new way to measure. And it's actually pretty important, and it extends into some other math classes you'll take after geometry is over. But I'm going to start out with just practicing with these first 5 questions and seeing if you can notice a pattern with them. I see a lot of glare here. It's really weird. All right, so a circle has a radius of 1 unit. Nope. There we go. A radius of 1. Find the length of arc defined by each of these central angles. Give your answer in terms of pi. Here's your reminder. Circumference equals 2 pi r. And then when we do our arc length, we just multiply by the ratio of the central angle to the angle of an entire circle, which is 360. So if we go here, for number 1, we have 2 pi r times 180 over 360. Now 180 over 360 is the same as 1/2. So 2 pi r times 1/2, those cancel out, and I'm left with just pi. All right. Number 2, 2 pi r times the central angle, the ratio of the central angle over the whole circle. Now I know 45 degrees is 1/4 of a circle. So this fraction right here will reduce to 1/4. So that's going to reduce to just pi over 2. And you can grab your handy dandy calculator and double check that, no worries. 2 pi r times the ratio of the circle. Now 270, we don't use that one quite as much, but that's actually 3/4 of a circle. It's 180 plus 90. Oh, I've changed colors. So that reduces to 3/4. I just don't want to get my handy dandy calculator out. That reduces to 3 pi, that's 23 over 2. Okay? And then let's go back to our 2 pi r times 360 over 360 is 2 pi. All right, these are actually called radians. I'll write that word down for you. It's another way to measure angles. And like I said, it's important. I've used it a ton in math classes outside of geometry. Another way to measure angles. When I start writing too fast, my pen gets all wonky. Okay, they're called radians. So whenever you see an angle measure with pi in it, it's measured in radians almost always. Okay, not always, but almost always. And what I see here is when you're measuring an entire circle, okay, the angle, the degrees, it's 2 pi. Okay, I should actually go this way because that's a much more common way to measure angles is counterclockwise. Okay, when you have just half a circle, that's pi. Let's do this. Whole circle, 2 pi, half a circle, pi. Okay, 3/4 of a circle, 3 pi over 2. That's beautiful. 1/4 of a circle is pi over 2. Okay, and I'm actually going to fix this one. I would hope that you're writing this down. There's a reason that I've started each arrow from that spot. Okay, if I looked at the coordinate grid, okay, anytime I draw a circle on a coordinate grid, I always start from this side, okay, because that's quadrant 1, quadrant 2, quadrant 3, quadrant 4. That's why I've started each one of these at this spot when I've drawn my arrows. All right, let's move on. All right, I'm going to read this first and then we'll work through it. So Diego and Lynn are looking at two circles, right here and right there. So little r, theta, little l is my length of my arc, the radius, and the measure of the central angle. Big R, big L, and the central angle hasn't changed because remember when things dilate, your angle measure does not change, it's congruent. Diego says it seems like for a given central angle, the arc length, let me see if I can get rid of that dot, there we go. The arc length is proportional to the radius. Okay, so arc length over radius, they're proportional. That is the ratio of little l over little r has the same value as the ratio of big L over big R. Oh my, you can, there we go. I will admit I'm having Wi-Fi issues at my home right now. So I'm recording with a hotspot. Probably not the best thing, but okay, the same value as the ratio big L over big R because they have the same central angle measure. Can we prove that this is true? Lynn says the big circle is a dilation of the small circle. Remember, dilates out. If K is the scale factor, then big R equals K times little r. So this is a dilation by a scale factor of K. So I can take little r, multiply it by K, and it becomes big R. So big R equals K times little r. And that makes sense. Diego says the arc length of the small circle is L equals theta over 360 times 2 pi r, which is what we just did in task 1. We said the length of the arc is 2 pi r times your central angle over 360. Okay, so that's what we said. I just wrote it in a different order, which is the order that I've written it in the whole lesson. So in the large circle, it's L equals pi over theta over 360 times 2 pi big R. So I'm going to write it again. Whew. It's right there. We can rearrange that as L equals theta over 360 times 2 pi rk because we just said big R equals K times little r. So this one I can rewrite as 2 pi K little r times theta over 360. Okay, substitution. So L equals K times L. All right, what does that mean? Where did everything go, right? Where did everything go? So how can I get from there? I'm out of paper. That's tragic. All right, so we've got little l equals this, big L equals that. So we can say that big L equals K times little l. All right, let me see if I can erase some things and move some things around. All right, I just moved everything up here. Okay, so you can push pause and check that out. I'm going to erase everything down here. I just need some more room. Okay, I haven't done anything except moved it up. Okay, so now we're just going to keep on reading. Okay, we will get this. Where are we? Okay, that's what I'm working towards. Okay, I can keep going, but I'm going to jump ahead of the problem. So Lynn says, okay, from here I can show that little l over little r equals big L over big R. I can show that those two things are equivalent. How does Lynn know that the big circle is a dilation of the small circle? Because the angle has not changed. How does Lynn know that big R equals K times little r? Okay, because it's a dilation with scale factor equals K, because theta didn't change. Why could Diego write L equals theta over 60 times 2 pi r? Because that's how you find the length of the arc, because that's what we've been doing for 2 days. When Diego says that big L is equal to K times little l, what does he mean in words? Well, the length of the big arc is equal to the scale factor times the length of the little arc. Okay, that makes sense. We're going to prove it algebraically, but that makes sense because of the scale factor. Why could Diego say that? Well, okay, what he means in words here, I guess I should be clearer, is the length, TH, I can spell, keeping it honest. Length of big L is the scale factor times little l. Then how can Lynn show that these are equal? That one's actually not quite as difficult. But just a second. All right, so now I am at a space that I have some room. For this problem, I'm going to go to the top. All right, so here we are. I've got this equation and this equation, which we've already talked about why they exist, right? Now, I'm going to take this and this. Let's talk about what things are similar. They both have a 2. They both have a pi. They both have a little r. And they both have theta over 360. This is the only thing that has changed. All right? So I'm going to take this equation and divide both sides by k. That gives me big L over k equals 2 pi little r theta over 360. And I have little l equals 2 pi r theta over 360. Now, when these two things are the same, I can actually set, so that right side of the equations are the same, I can set the left side of the equations equal to each other. L equals big L over K. All I did is take the right side of the equations, since they're equal, and substitute. Okay? It's just like saying that, let's say W equals Y and Z equals Y. Well, since they both equal Y, W equals Z. I have L equals Y and L over K equals Y, so L equals L over K. Okay, so that's how we come up with this part and this part. We're just saying that big L, ooh, silly me. Now I can multiply both sides by K, sorry. Big L equals little l times K. It means your big arc is equal to your little arc times your scale factor, which intuitively makes sense to us. Forgot to finish. All right, now, what about Lynn? What is she doing? All right, I'm going to rewrite these two little equations. L equals 2 pi r theta over 360. And big L equals 2 pi r k theta over 360. All right, now she's saying that, let's see, I'm going to, should have left myself more room. And this is first equation, divide both sides by r. Because again, we know that these three things are the same in both equations. So I'm going to divide this by r. Those are check marks, not r's. Sorry. We should do this. So I have L over R equals 2 pi theta over 360. Over here, let's divide both sides by RK. I need a big R here. We need to revert back to the first equation. Now we have big L over big R equals 2 pi theta over 360. So now the right side of the equations are equal to each other. So I can say L over R equals L over R. So she just used equations and manipulated them in a different way, and they're both equal. All right, so what are we doing with this? Well, first of all, it was a great review on algebra, and we are going to do something with this, okay? All right, let's use what we just learned, which is L over R equals L over R. So I can say, I got little and big, 7 pi over 14 equals 10 pi over 20. Let's simplify that. This simplifies to 1/2, so pi over 2, and this also simplifies to 1/2, pi over 2. So what was our scale factor here? Looks like it's 1/2. So to keep these proportions, so these are dilations because we've shown that the left and the right side of the equation are equal to each other. What else can we show here? I'm going to check. See, our constant of proportionality between the radius and the arc length is pi over 2. Cool. How does the example relate to what you proved in the activity? We proved that L over R is equal to L over R, and they're both equal to pi over 2. Cool. All right. So let's do the next task statement. So here it says defining radians, and like I told you in task statement 1, that's what radians are. So suppose we have a circle that has a central angle. The radian measure of the angle is the ratio of the length of the arc defined by the angle to the circle's radius. That is theta equals arc length over radius. The image shows a circle with radius 1 unit. We can't do this, okay? It's pretty cool though. And what this exercise does, it gives us just a tangible way to show how this is equal, how radians work. But radians, we can say theta equals what it says there, the arc length. This is what I need you to remember. Over, it says the radius. All right? And that's all we can do in this part, this third part. Okay, here's a very good example. The central angle is 1 radian on this example because my arc length is 1 and my radius is 1. I feel like that's sort of a wah, wah, wah for this example, or for this lesson, but that's okay. We're good.